Hi there, and welcome back. This is Chapter 4 in the Essential Cosmic Perspective book, Making Sense of the Universe, Understanding Motion, Energy, and Gravity. We're going to go through this pretty quickly. There's just a few slides I want to talk about here. So we're going to describe motion and examples of motion in everyday life. How do we describe it, and how is mass different than weight? So here are precise definitions to describe motion. There's speed. Speed is the rate at which an object moves. It's distance divided by time. This does not include a direction. Velocity is the same thing as speed, but has a direction. So you see the example here, 10 meters per second due east. That's the difference between speed and velocity. And then acceleration is any change to a velocity as you speed up in your car. Acceleration of gravity says that all falling objects accelerate at the same rate, not counting friction of air resistance, of course. On Earth, the value of little g for gravity is about 10 meters per second squared, and the speed increases 10 meters per second with each second of falling. So you drop a ball off of a building, after 1 second it's going 10 meters per second, and after 2 seconds it's going 20 meters per second. Now Galileo showed that g, little g, is the same for all falling objects regardless of their mass. And this was demonstrated on the moon of the Apollo 15. They took a feather and a hammer and dropped them at the same time, and they both fell at the same rate. Momentum and force are a little bit more complicated. Momentum is the mass times the velocity, and a net force, or a change in force, changes the momentum, which generally means an increase in acceleration, the change in velocity. And the rotational momentum of a spinning or orbiting object like a planet is known as angular momentum. So how is mass different from weight? Mass is the amount of matter in an object, stuff that makes it up, and the weight is the force that acts on an object. You are weightless in a free fall. So why are astronauts weightless in space? There is gravity in space. The weightlessness is due to a constant state of free fall. They are constantly free falling around the Earth at the exact right speed, which is about 17,500 miles an hour. Now Newton's laws of motion. How did Newton change our view of the universe, and what are Newton's 3 laws of motion? Well, Newton realized that the same physical laws that operate on the Earth also operate in the heavens, one universe. He discovered the laws of motion and gravity, and much more. He experiments with light, first reflecting telescope, and in his spare time, the dude just invented calculus off the top of his head. He just did. Alright, Newton's first law of motion. These laws are very important. You'll need them on the quiz, you'll need them on the exams, and the final. Newton's first law of motion. An object in motion stays in motion unless acted upon by an outside force. That's my description of it. The text says an object moves at a constant velocity unless a net force acts to change its speed or direction. So I've always learned it this way. An object in motion stays in motion. An object at rest stays at rest unless acted upon by an outside force. Newton's second law of motion is an equation. Simply it's force, or F, equals mass times acceleration. And so that's what we calculate force with. Newton's third law of motion is for every force there's an equal and opposite reaction force. So if you have a shuttle shooting out its gas through its rocket boosters down, it's going to push it up. If you push against a wall, it's going to push back against you. So we learned that Newton changed our view of the universe by discovering the laws of motion and gravitation. He realized these same laws of physics were identical in the universe and on Earth. And Newton's 3 laws are, number 1, law 1, object moving at a constant velocity if no net force is acting on it. Or we could say an object at rest stays at rest, an object in motion stays in motion unless acted upon by an outside force. Law 2 is the equation force equals mass times acceleration. And law 3, for every force there's an equal and opposite reaction force. We're going to learn about the strength of gravity, how do Newton's laws of gravity extend to Kepler's laws of planetary motion, how do gravity and energy together allow us to understand orbits, and how does gravity cause tides. Actually, we'll probably skip the tides for it. The universal law of gravitation, the grand scheme of things, says that every mass attracts every other mass. Attraction is directly proportional to the product of their masses, and attraction is inversely proportional to the square of the distance between their centers. Well, what does that really mean? You see the equation here. You don't need to know this equation. It says force of gravity is equal to big G. This big G is a constant number. It's a very small number. It's just a number thrown in with a bunch of different units attached to it to make all the units work out to the right figure. We have a mass of one object times a mass of a second object, which is inversely proportional to the distance squared.